You have to know some angles. This is memorization, which I hate, but anyway, the practice exam says that we need to know some angles. So let me put down these triangles. If we have a triangle like this with angle pi over 6, then the sides are like this. If we have a triangle like this with pi over 4, it's a bad triangle. Then the sides are like this, 1, 1, and then 1 squared plus 1 squared, square rooted is root 2. And if we have a triangle with the angle pi over 3, it's kind of like this. And it's similar numbers to this, but it's changed around. So this guy is this guy is this, and this guy is this. And the reason I tell you this is that you have to know the sine, cosine, tan, or whatever of these angles, pi over 6, pi over 4, pi over 3. That's what it says at the start of the practice exam. And the questions have that. You need to know these things. But once you have these triangles, you have any trigonomic function applied to these angles, right? Because whatever trigonomic function you want, for example, sine of pi over 6, you know that sine is equal to the opposite side, divided by the hypotenuse. So it's 1 over 2. And cosine of pi over 6, it is the adjacent side divided by the hypotenuse. Like this, This guy is easy to remember or understand because if you have equal length sides 1 and 1, then that's what you'll have for 45 degrees, and therefore sine of pi over 4, opposite divided by hypotenuse, 1 over root 2, same for cosine. This guy's the easy guy. Same thing here, whatever you want. If you want to know cosine of pi over 3, adjacent divided by hypotenuse, 1 over 2. So to know all the trig functions of whatever of these three angles, all you need is to have this picture in mind. Oops, or maybe these three pictures. This guy is easy, nothing much to think about. So the only thing you really need to remember is the root 3, 2, 1 are these Pythagorean triple, in that if you square root 3 plus 1 squared, you get 4, which square root is 2. And then this guy is just very similar to this guy, but the long side is now the opposite side. So actually all you need to remember are these numbers, root 3, 2, and 1 on the sides of a triangle. So I claim there's very little to remember here. If you can just remember this, what we call a Pythagorean triple, because these are the sides of a right-angled triangle given by root 3, 1, 2. You can figure out all of these guys because you know that this pi over 6 has to be the thin angle, so the root 3 has to be on the bottom. Do you see what I mean? Give me a thumbs up if that's making sense to you. Okay, good. So not much to remember. You can have all the trig angles, all the trig functions on these angles, pi over 6, pi over 4, pi over 3 from these three pictures. Draw them for yourself, convince yourself, and then you'll be fine. You don't have to remember a long list of things. Just need to remember essentially one thing. Okay, cool. That's the first thing I wanted to say. Second thing I wanted to say is that I saw a question on average, which we didn't discuss, and I thought that was going to be cut from the syllabus. It was meant to be last semester, but anyway, it seems to have appeared again. So we might have a question about average. So I need to talk about what average is. So let's just do that briefly. So given some function f from AB into the real numbers, the average of f is this thing. It's the integral from a to b f of x dx over the length of the interval. like this. And I'm going to abbreviate average to just AV. Yes? Rewrite it. Yes. Given f from the interval a to b, is it my handwriting or is it the pen is fading? That's the real numbers. Thank you for the question. It's the real numbers. Thank you. All right, so this is the average, and let me try and explain why. So I'm going to abbreviate this now to AV of f. So from now on, this is AV of f. Okay, just for simplicity. And then what does that thing say? That it implies that AV of f is equal, or AV of f times b minus a is equal to this integral from a to b f of x dx. Okay, let's draw a picture. So if we have our interval a to b, okay, and let's make our function positive, just to make a nice picture. Then we know that the integral is just the area underneath the graph above AB, right? So what does this thing say? It says that this guy, this number, times b minus a is equal to this area, yeah? So we get a different color. There we go. So let's represent what this thing is. So if we put a rectangle whose height is given by AV of f, right? Like this in the blue. Yeah. Then a rectangle's height is AV of f and whose base is from A to B. That thing would have area given by this. Yeah. So the area of the rectangle in blue here is given by this thing. Yeah. Yeah. And that thing is like the area underneath the graph, which will mean that the average is something like here, yeah? Something like here, something which is less than the highest value, bigger than the smallest value, yeah? And if you think about it, this is the natural notion of average. This is the correct thing. So if we were just doing this with a collection of numbers, we would just go the average of A1 plus A2 plus blah, 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 AN is just adding them all together and dividing by n, yeah? But integration is a generalized form of addition where we add over this infinite set, which is given by all the numbers between a and b, yeah? And then we divide by the length of the interval a and b. So this thing is a natural generalization of this thing, okay? So a common mistake is to forget to divide by the length of the interval and just take the integral itself. That's not the average. That can be something completely different. If we have a very small, thin interval, then this area can be very, very small, but the average of the function doesn't have to be small. Yeah, so don't forget to divide by the length of the interval. So does this make sense? Does this seem convincing to you that why this thing should be the average? Yeah? Cool. All right. So that's what the average of a function is. One of the questions asks us to find the average, and just getting the definition right. Just do the integral divided by the length, and you're all set. You're fine. All right. Let's do some of these practice problem questions. Cool. All right. So let's do this question. So we have y of x equals the square root of 1 minus x squared, and we are integrating from 0 to 1 of y of x dx. That's our task. So look at this. What method are we going to apply here? What kind of, so we talked about this last time in the strategy for integrals. What's this calling out for? Yep, trig sub, yeah? Because it has this structure of the square root of plus minus a squared plus minus x squared, yeah? So this is a natural trig sub guy, yeah? So we're going to figure out which trig sub guy it is. We have a sine squared of x plus cosine squared of x equals 1, and our tan squared identity. But if we look at this guy, we write that, let's write cosine. Cosine squared of x equals 1 minus sine squared of x. Yeah? And we see that that is the thing that we want. We want to stick in x is equal to, let's call it sine of theta. Yeah? To exploit this structure to kill the square root. Yeah? And then if we do this, dx by d theta equals cosine of theta. And then we get a theta, or cosine of theta, d theta to deal with. So we have dx equals cosine of theta, d theta. Yeah. And we're going to turn this guy into an integral in respect to theta. So let's worry about the limits in a second. Firstly, this is our function. So it's like 1 over 1 minus sine squared of theta. Like this, the dx becomes cosine of theta, d theta. And now let's think about the limits. So this thing here, let's put it over here. This thing here is saying x is sine of theta. So we know that theta is equal to arc sine of x. Right? And then we're going to put in the values for x. So when x is equal to 0, what is arc sine of 0? That's just 0. Yeah? And then when x is equal to 1, we have to ask ourselves, what's arc sine of 1? Oh, it's not 1. It's actually a half. It's actually a half. I miswrote this. So here we go. So it's arc sine of a half we have to think about. So arc sine of a half is equal to theta. In other words, sine of theta is equal to a half. And now we're going to look at our triangles that we have here. Yeah? And it's going to be one of those angles because those are the ones they told us to know, right? To be aware of. Yeah. And if we look at this one, so if sine of theta is a half, right? Sine is the opposite divided by hypotenuse. We're going to identify which of these triangles does that, right? And which do you see? It's going to be this guy. Yeah. Yeah. So then that means that this implies that theta is equal to pi over 6. Do you see what I mean? Yeah? Give me a thumbs up if you're with me here. Do this if anything's unclear. So, those of you who haven't turned on your video, whatever I can't get any feedback from you. So, if you want to send me feedback, I need to see you because it's like. Or you can just speak out loud and just say if you'd rather do that. All right, so we're turning this into limits in theta. So this is not a half. This is pi over 6 right here. Right. So from these limits in x, these now become limits in theta, and then this is like this. Yeah. Cool. And then what is this? This is the integral from 0 pi over 6, and then we just have cosine squared of theta. D theta, yeah? And then because cosine squared we learned how to do, yeah? We have these double angle formulas that is also told us that we should know. Because of the pandemic and online exams or whatever, you have a cheat sheet, so you can actually put this stuff down. Going forward, when this problem is over, you won't have, so I'm going to teach you as if you don't have the possibility of having a cheat sheet. So I'm going to try and teach you stuff like this, where you're not memorizing stuff or having to write stuff down, where you just have a couple of ideas that will recover stuff. But these guys, I don't have any good suggestion as to how to recover this. But we have this identity, cosine squared of theta equals a half. I think it's 1 plus cosine 2 theta. Let's check that. Yeah. So this is very small. We probably can't see it well, but I'll rewrite it. This is the identity that we have. So we will use this. And we integrate from 0 to pi over 6. And then we'll put this a half outside here, and then this thing becomes 1 plus cosine of 2 theta d theta. Yeah? And now we're in good shape, because now we can integrate everything here. Right? Now we can integrate everything here. Yeah? Because what's the antiderivative of cosine 2 theta? We ask ourselves what we differentiate to get it. Well, if we try sine of 2 theta, we have it as extra 2. So we just divide by 2, and that gives us what we want, right? Yeah? So shall I continue this, or are you happy with this from this point onwards? We had this thing. We had the integral from 0 to pi over 6. We had this 1 over 2 we pull out. We have this thing. Cosine of 2 theta d theta. That's where we were. All right, so if we look at this, what do we see? So 1 over 2, let's this, pi over 6 to 0. Then the antiderivative here is just theta. And then what is this guy going to be? It's going to be sine of 2 theta over 2. Oh, I see why it's worth continuing this, because there is an extra thing to think about. So this part is fine, right? So evaluating this part, so we're going to have 1 over 2 times just pi over 6 from this part. And then we're going to have like 1 over 4. And then we want to evaluate from pi over 6 to 0 sine of 2 theta. Yeah? But then we have this other identity that sine of 2 theta is 2 cosine theta sine theta, right? So we have sine of 2 theta is 2 cosine of theta sine of theta. Yeah? So we can put that directly into this thing. So when we evaluate 1 over 4, so now let's just take out this factor. So it now becomes, let's write this like this. So this guy over here in the blue box, the blue box becomes 1 over 2, and then the integral of pi over 6 to 0 sine of theta cosine of theta, like this. And then we have to use our triangle again, right? So this was the pi over 6 triangle, right, where the sides are this root 3, 1, and then 2. Yeah, so you just have to remember root 3, 1 as the opposite and adjacent, and then 2 has to be the hypotenuse. And then because the pi over 6 is the thinner angle, the root 3 is on the bottom. Yeah? So sine of pi over 6, I think that's probably the thing we just did. Sine of pi over 6 is the opposite divided by adjacent, it's 1 over 2. And then cosine of pi over 6 is the adjacent divided by hypotenuse, so it's root 3 over 2, like this. So then we can put those numbers in. So we have 1 over 2 times 1 over 2 times root 3 over 2. So we have root 3 over 8, like this. No? Everybody happy? So this blue box is equal to this thing, which is equal to this thing, which is equal to this thing. And therefore, the entire answer to the question, so let's call this thing star. That's where we were before. So star is equal to the addition of these two things. So it's going to be pi over 12 plus root 3 over 8. And that's the answer. Everybody with me? Yeah? Do this if anything's unclear to you. That's true. That's true. Yeah. That's true. I didn't think about that. Yes. Because if we consider about this thing, then it is this pi over 3 angle, yeah? And the pi over 3 angle is where these sides are flipped, so it's root 3, 1 over 2, like this. So indeed, sine of pi over 3, which is what we would have when we do this, is this thing. It is the opposite divided by hypotenuse, so it's root 3 over 2, and then it's going to be times a half, and we get the same answer. So indeed, yeah, you're right. Yeah, I wasn't thinking about that, but that's a simplification, so a good suggestion. Yeah. Any other questions? Cool. All right, let's do another one. Let's do question 2E, perhaps. Trying to find the ones that are, no, let's do just the hardest ones. Let's do G, because we probably don't have that much time. Let's do G. So this guy, so if we look at this, to begin with, it looks kind of difficult because it doesn't look like any recognizable form. But following step 1 of the strategy, we will try and do some algebra to get it into something that we understand. So it's obviously a rational function. It's a polynomial of a polynomial. Yeah. So what we need to do is to try and understand what kind of rational function it is so that we can classify it, yeah? So you try and factor the bottom because that's how this stuff works. We classify according to what we have on the bottom. So star is equal to this thing. And then what we do, if we pull out an x, we're going to have x, and let's write it over here. So we have x squared minus 2x plus 1. And then this thing we can factor as x minus 1 squared, right? So then this is x minus 1 squared dx, yeah? Cool. So now we see it's in the form that we instantly recognize what to do with, right? What case of this partial fraction stuff is this? Or better to say, what do you see at the bottom here? What do we have here? What are these things here? It's case 2. And what are these things? These are linear factors, right? These are linear factors, yeah? And we have one by itself and one which is repeated, yeah? So it's case 2. And let me put that. So case 2. So we know that 4x plus 3 has to equal to x minus 1 squared. And we're going to have an a that takes care of this guy. And then we're going to have a b that takes care of the first power of this guy. And then we're going to have a c that takes care of the second power, like this. Yeah? And then our job is to find these a, b, and c, because once we find the a, b, and c, then we can just do it. Yeah? Cool. And then we can only find the a, b, and c when we make a common denominator. So let's do that. So we're going to have to multiply top and bottom by x minus 1 squared here. So I have x minus 1 squared. Top and bottom by x minus 1 times x here. And then top and bottom by x here. And then all of that stuff is under this common denominator, x minus 1 squared. Yeah? See what I mean? So this thing implies that this top line is the same as this top line because we multiply through by the denominator. So we're going to expand out the bottom here and put it in the form of some coefficient in front of the x squared, some coefficient in front of the x, and some coefficient, well, some constant, the constant term in front of the x to the 0. So running out of space. I'm going to try and do this all in one go. So what's the x squared stuff we pick up? We're going to have an x squared from here, an x squared from here, and that's the only thing, right? So we're going to have a plus b, say it louder, x squared. Yeah, that's the only x squared we see here. Then we look for the x's. What x's do we have? We're going to have a minus 2ax from this thing. Yeah? Let's put it in, minus 2a. Yeah? And then we're going to have a minus bx from this thing. Yeah? And then we're just going to have a plus c here. Yeah? And that's the x. And then let's look for the constant term. We're going to have an a here. Yeah? No constant term here and no constant term here. Yeah? Give me a thumbs up if you're following, people. Okay, thank you. So this is just equal to a. So this quadratic has to equal to this quadratic, which is 4x plus 3. Yeah? So we have that these guys are equal for every x, which implies that we have these three different equations, because this is only true. So I'm going to put the equations and then we'll solve them on the next board. This is only true if this a plus b is 0, because there's no way this quadratic can be equal to this thing unless a plus b is 0. This is what we discussed when we did this topic. Yeah? Yeah? Just because if this is true for all x, there's no way this quadratic thing is equal to this linear thing if this is non-zero. Yeah? So we must have that a plus b is equal to 0. Yeah? That's one of the equations. The next equation, we must have that the linear terms agree. Yeah? Because we know this y is 0 now, so these two linear terms here and here have to agree, otherwise there's no way this equation is true for all x. So then we have the equation minus 2a minus b plus c is equal to 4. Yeah? And the final equation all the way down here, I have to put it, is just that the constant terms agree, which means that a is equal to 3, which is convenient because then that just tells us what a is. So we have these three equations. Huh? We have these three equations, and we have three unknowns. Since a is given to us now, we just have two unknowns. We're going to have to use those to find the b and the c. Then we plug them in here, and then we can solve it. That's our strategy. Yeah? All right, we're going to raise the board. We're going to go from this point on the next board. A plus b is equal to 3. We had that minus 2a minus b plus c is equal to 4, and then a is equal to 3. So obviously we know what a is. Then we do the algebra to make this as simple as possible. Because a plus b is 3? No, it's a plus b is 0. A plus b is 0, like this. So to me, an obvious step would be to add these two guys, because it would just kill the b. So let's add this guy and this guy, add them together. So I told you to put numbers on these guys, so let's do that, even though I don't have much time. So if we do 1 plus 2, then this goes to minus a plus c is equal to 4. Yeah, because the b's cancel, which is for minus a. A is equal to minus 3, so this implies that c is equal to 7. Yeah? And then we need to figure out b. B is just going to be minus 3 because of this equation here. And then that's all we need, because then our original integral becomes this thing. So our original integral is now 3 over x minus 3 over x minus 1, and then plus 7 over x minus 1 squared dx. And now we're fine, right? Because we can do this. So then this is equal to 3 log of the absolute value of x minus 3 log of x minus 1. And then what do we differentiate to get this? If we differentiate x minus 1 to the minus 1, we're going to have the right power, but we'll have a minus sign in front. So what if we try this? Let's do minus 7x to the minus 1 to the minus 1. If we differentiate this, then this becomes plus 7, the power goes down, and it's everything that we want. And then plus constant c, and then that's it. That's the answer. Yeah? Yeah. So it looked kind of tricky, but it actually, after we factored it, we could see what to do. Okay, let's look for tricky ones. Okay, let's do this guy. This is E from that section. This is not counted. This is E. We have x and then tan to the minus 1 of x dx. Okay, so solution. So this isn't so obvious, at least to me, what to do, but I do notice that if we differentiate tan to the minus 1, then we have this nice thing, 1 over 1 plus x squared, right? And if we integrate this guy, we get x squared. So if we do this thing of calling this guy v prime and this guy u, then switching to v u prime, we get a rational function. And rational functions we can do, right? Rational functions we have the machinery to do. Yeah. So it's fairly quick to let v prime be this guy, and you go and just in your head ask yourself if you get something better when you try an integration by parts, when you swap from this to v u prime, and you do. So that's how I would suggest you would find that this is the thing to do by integration by parts. And let's see what happens, because it's not that trivial. So if we do this and star, so if we integrate this guy, we're going to get x squared over 2. So this guy, we're going to do uv. So we're going to have x squared over 2. So I prefer to write arctan, because sometimes tan to the minus 1 students think of as 1 over tan. So well, the question wrote it like this way, but I'm going to write arctan from now on. So this is the vu, and then minus, again, integrating this, we're going to have x squared over 2, and differentiating this thing, we have 1 over x squared, 1 over 1 plus x squared, like this, dx. And let's pull out this factor of a half in the front here. Yeah? Everybody with me? Cool. So this guy is not so great because it's not actually a proper rational function. It's not actually a proper rational function. Yeah? And proper rational functions are the ones that we can apply this stuff to. But there's a kind of a trick we can apply. So this whole thing is x squared over 2 arctan of x minus 1 over 2. And then let's do this trick. Let's write this as x squared plus 1 minus 1. Because plus 1 minus 1 doesn't do anything, right? And over this, 1 plus x squared. And if we do that, then this thing, let's not rewrite more than we need. Let's put this guy in a box. So the stuff in the blue box, put it down here. So the blue box becomes what? It becomes the integral of just 1 minus 1 over 1 plus x squared. If we think about it, what we just did was a very kind of a quick way to do long division, because now we have a polynomial plus a rational function, right? So we did a kind of like quick long division to put it in the form that we like. Yeah. And this guy we really do like because we know what the antiderivative of 1 over 1 plus x squared is. Yeah? Yeah, because we just talked about it. It's arctan. So then this thing just becomes x minus arctan of x like this. Yeah? So then we can do everything in the blue box. So then the entire thing, so I'll put this back into this, the entire thing becomes x squared over 2 arctan of 1 over 2, and then minus a half times this thing. So minus 1 over 2 x minus arctan x, and then everything's plus constant c. Clean this up a little bit. Let's maybe do this. Oh, something is wrong. Why did I put a half here? No, this is just x. So this is arctan of x. And what do we have? We have x squared over 2, and then plus 1 over 2, and then just minus x over 2, plus constant c. And that is how we do this guy. Everybody okay? Everybody happy? Yeah? How am I doing for time now? $11:04. All right. I want to do another one just for those of you who want to stick around. Stick around if you want to see another question. Otherwise, I'll see you on Monday. I have office hour on Monday, so it's your chance to ask me any final questions. Keep reviewing, keep working, and have a great weekend, those of you who are leaving. All right. Let's do at least one more. Question 4. Let's do this. Integral from 0 to pi over 2 cosine of x log of 1 plus sine of x dx. Okay, so you should hopefully quite quickly think u-sub, because you see the sine and you see the cosine x dx. No? This is a natural u-sub this is a natural first step to try and do this. So solution, let's call this thing star as normal. Let's let u be sine of x. Then du by dx is equal to cosine of x. So du equals cosine of x dx. And that's the structure that we have. And now we're going to try and turn this thing into an integral with respect to u. So then star becomes, we have to change around stuff. So when x is equal to a half, when x is equal to a half, we're going to put a half into here. So sine of a half, the graph of sine, I say half, I mean pi over 2. Sine of pi over 2 is just 1. So then these limits go from 0 to 1. And then we're going to have log of 1 plus u du. Yeah? Give me a thumbs up. Go ahead. That's a good idea. That's a much better thing to do. Yeah. So I was going to do, the next step was do another sub with this thing, but much better to do it this way. Indeed. And that changes nothing with the du, but now we just have log and we change the limits. And now they go from 1 to 2, I think. Yeah, so then when x is equal to 0, we get 1. When x is equal to pi over 2, we get 2. Good suggestion, thank you. So we have 1 to 2. Excellent. And now we look at this guy, and this is an example of integration by parts that we did. That this is one of these things where it doesn't look like there's a product, but there is a product. It's 1 times log. Yeah? And if we do integration like by parts in this way, so then we have to let the u be the log, because we can't integrate log. That's the whole problem, right? So u has to be log, and then v prime has to equal to 1, right? And then v prime equals 1. And then we can to this guy from 1 to 2. And then the antiderivative of 1 is just x, or u, because we're doing u. So it's u log of u. Yeah. And then minus the integral from 1 to 2. And now if we differentiate this guy, we get 1 over u. And then we integrate this guy, we get u. So we get 1 over u times u, which is just 1, like this. Yeah? And then we just put the limits in. So we're going to have 2 log of 2, put log of 1 in here, so we get 0. So that thing is just 0, and this thing is just this. So this should be our answer. And it is. Okay, everybody good? Everybody happy? All right, good. So, if you haven't done all of these questions, please do them all. Do every single one of them. And only after that, look at the answer. So it's very easy to look at the answer and think, oh yeah, I would have done exactly that. But you won't necessarily have done that. So I've taught calculus many, many years, and every time I do it, I throw away my notes and I write the solutions again before class, because no matter how much I'm sure I would do exactly this thing, unless I write it out, I can get it wrong. I can go in some tangent. So you have to do the same thing. It's really a mental illusion that when you see a solution, you think you would have done exactly that. You have to figure it out for yourself to really be sure. So work through the problems. Don't look at the solutions. Work through them all, every single one of them, and then check your answers. And then the stuff that you get wrong, focus on that stuff. Go to the end of that section, do the ordered exercises, get that stuff right, close your gaps. You people remaining, I'm guessing they're more motivated. You want to do well, to take this advice. Close your gaps, and you will be in a good shape on Monday. It will go well for you. Okay, I'll send an email about a potential weekend review session this afternoon, and if I don't see you then I'll see you on Monday. Have a good weekend, people.